So the family of all antiderivatives of a function f of x is the indefinite integral of f with respect to f, and is denoted the integral of f of x dx equals capital F of x plus c. So that whole list of integrals that I gave you, those are all indefinite integrals. And so big F is the right-hand side of that. Okay. Big F is the right-hand side of that table of integrals, and then little f is the derivative of big F, so working backwards. So we've been using our knowledge of derivatives to evaluate integrals since 6.3. Okay, I've just relied on you being able to find the antiderivative and then take that, what you think is the antiderivative, just like kind of guess and check, trial and error, a little bit of trial and error, and work backwards from that. And then I've shown you just a couple tricks in terms of dividing by the derivative of the inside. That's about it. Or with the power rule, raising it up one power and then dividing by that power. We've looked at that specifically as a technique for reversing the power rule, but we haven't formally been shown how to use what's called U substitution to integrate. So now, once you learn U substitution, it opens up a whole new world of integrals that you can do. If you look at the back of your book, you'll see hundreds of integral formulas in there. So, I mean, they have just tons and tons of appendices of formulas for integrals. But we're just learning primarily the ones on that sheet. All right. So the big question is, what happens if we have an integral that does not quite fit one of the ones on the table of integrals? We've actually had several that haven't. And the answer to that is we've got to do some kind of rewrite. So algebraic simplification, sometimes simplification, at least in terms of integrals, simplification doesn't mean condensing it into one thing. It usually means separating it out into many. Because of that, remember the property of integrals, it says I can go ahead and integrate each part and then add them up or subtract them. So we're using that a lot in integration. Also, there are trig substitutions, algebraic rewrites. So you got to be, your factoring's got to be good. You got to be able to complete the square. You have to be able to do long division. Tons of different rewrite methods to get them to match up to your table of integrals. So it's kind of a basic one. You have the integral of sine of x e to the cosine of x dx. And so we're going to decide what u is going to be here, and what needs to happen is whatever we decide u is, its derivative has to be part of the integrand. So do you have a guess as to what u might be in this particular function based on your chain rule experience? What's that?
Extremely complicated.
No, it's not extremely complicated. No. It is cosine of x, yes. Yes. What leads you to believe that u might be cosine of x here? I mean, it's either cosine of x or maybe sine of x, right? But yeah, cosine of x is the power on e. So what is the derivative of cosine x? Negative sine of x. And hey, look at this. Right here, you'll see that we kind of have negative sine x dx in here, right? We're just missing one little thing. It's negative sine. And with integration, I have no problem adding in negative signs, okay, into the integrand. I just have to balance it out with the negative sign on the outside. And I have no problem putting in constants. Like I could stick a 3 in here, as long as I balance it out by putting a 1/3 out in front of the integral. Okay. So the idea behind u substitution is you pick a u so that we can rewrite this function, but you need to pick a u whose derivative is in the integrand. Okay, the integrand is what you're taking the integral of. Okay, so u equals cosine of x is actually going to work. The derivative of cosine of x is negative sine of x dx, and so we have to do a little bit of wishful thinking here. I wish there were a negative in my integrand. Like the Magic Kingdom here. I'm going to make your dream come true here. I'm going to stick a negative in the integrand. And I'm going to do it in such a way that it's algebraically sound. So I'm sticking my negative in front of sine x. here's my dx over here. By sticking the negative in here, sine x dx, I match du exactly. Okay. And then I need to go ahead and do e to the cosine of x here. So what I've done is I've added a negative out in front of the integrand to balance out the negative that I added in here. So negative times negative is positive 1. I have not changed the value of the integral at all. And I said integral on purpose. I'm talking about the whole thing when I say integral with the integral sign. Integrand is just what comes after the integral sign. So I have not changed the value at all. And actually I need to, the way I like to think about it is I don't ever do the u substitution, just like with the chain rule. I just do a rewrite like I've done here. But if I do my u substitution, I think we can find everything in the substitution in my integrand. So this would be equal to a negative integral. Okay, the e to the cosine of x becomes e to the u. And then everything I'm highlighting, whoops, no, not that. Be careful with my highlighter. Get rid of this highlight. So everything I've highlighted becomes what according to my u substitution? Du, yeah. All of that becomes du. So I have now taken this original integral and made it match. I think it's number 3 or 4 on your integral tables. If you call it your integral tables, you might want to have those out. What I've done is I've matched your integral table. I've even used a u. That's why they use u's, is because of this method of u substitution. So which one is it on your integral table?
4.
4. Okay. Number 4. What's the integral of e to the u?
U.
Yes, this is every mathematician's favorite function to integrate and differentiate. Yeah, the integral of e to the u is e to the u. And I have a negative sign out in front of it. And then one more step. I started in x, I need to end in x. Yes. So it's negative e to the cosine of x plus c. And we've actually done integrals like this, but I haven't formally said, let's make a u substitution for the power on e. I've just kind of had you check whatever your antiderivative is by taking the derivative, looking backwards. You know, that hasn't worked so well for some of us. But it really is, you have to make it fit one of those forms on the table of integrals. Or more globally, the tables of integrals that exist in the back of calculus books. So, any questions on example 1? The negative sign had to be in there so that if I take the derivative of this thing, it will match this whole integrand. So let's check it with differentiation. Derivative with respect to x of negative e to the cosine of x, and then we can have the plus c on there. What's the derivative of negative e to the cosine of x? We match it, yep. So it's negative e cosine of x, and then we take the derivative of the inside. So here's where the sign comes out. Derivative, yeah, negative sine of x, and then plus c, the derivative of the constant is 0. Does this equal the integrand I started with? Yeah. So that sine of x has to be in there for us to be able to integrate this when the power is cosine of x. If the power wasn't cosine of x, we wouldn't need it in there. But on these u substitution problems, in order for the derivative to equal the integrand, we have to have du in this integral with whatever u is, or e to the u. It does. I mean, that's the short answer. It goes away, but why does it go away? Because I'm able to rewrite this as the integral of just e to the u du. And so yes, it does go away. All right, example 2. Look at that integrand. Do you have a guess as to what might be u? Yeah, stuff inside the radical. You're right. Stuff inside the radical. Because what's going to happen here? Well, first of all, here's how kind of have an idea here. Maybe you can share, Ethan. How do you know stuff inside the radical? How is this going to help us relate to the x squared outside of it?
You see, don't know like this straight up integral for the inside of it.
Sure, we don't know an integral for, we don't have, if you look at your integral table, right, straight up, we don't know. So he's right, there isn't one, and you can flip through all the appendices and stuff, maybe you'll find one for square root with something out in front of it. You know, somebody's just kind of taken the U substitution rule and then created another formula, basically. So, but there isn't one on there. So we have to rewrite it somehow. The other way you can tell is what's the derivative of 2x cubed? 6x squared. Ah, there's x squared. It only is missing the 6 in front of it. But I just told you, I have no problem making your wish come true and sticking the 6 in front of the x squared, right? As long as I put a 1/6 out in front, because 1/6 times 6 is just 1. So, you know, I'm just using some rules of algebra to rewrite it. So he's right. U is equal to 5 plus 2x cubed, and du is 6x squared dx. And be sure to attach the dx, because the dx needs to go away when we do our u substitution. It needs to disappear as well.
Why don't you put the square root over it?
Not yet.
So you just,
Not yet. The square root will be over my u when I put u in. Okay? And then square root of u is the same as u to the 1/2. Can I integrate u to the 1/2?
Yeah.
Yes, by rule number 2 on your integral sheet. So it looks like this. I like to rewrite it first. So I'm going to rewrite this integral. So under the square root sign, I'm going to put 5 plus 2x cubed. I still have my dx in there. I need to put in a 6 here in front of my x squared, and also a 1/6 out front. So I think I have all of the components here. There's my 6x squared. See the 6x squared dx is in there. 5 plus 2x cubed will get replaced by u, and then I have my 1/6 out in front that I have to use to balance out the 6 that I stuck in there. So if I rewrite this, in terms of u, I would have 1/6 the integral of the square root of u, that's what all that becomes, and then you see the 6x squared in the dx. So this, along with this, all becomes du. So all of what I highlighted becomes du. Yeah, sometimes you could even probably stick the dx over here, but the common practice is to put the with respect to what variable at the end. But these go together. And this entire derivative has to be contained here. Now this u substitution will not work if you don't have du in the integrand. It can differ by a constant only, not by a variable. You can't add variables into this. Okay, if you need to add a variable in, then you need to try to integrate it by another method. There are other methods you can use to deal with that. But it can only differ by a constant. So you can only be balancing it out with constants, okay, or negative signs. Is that clear? So on this whole u substitution method, if you're having to add in a variable to make it match, you can't do that. All right, so what is the integral of square root of u? Maybe we should think of it this way. What's the integral of u to the 1/2? Okay, raise it up to u to the 3/2, and then divide it by 3/2. Let's see, so let's clean that up. What does that end up equaling? What is it? 1/9 u to the 3/2. Let's see. So the 3/2 is the same as multiplying by 2/3. which is 1/9 u to the 3/2 plus c. And what am I going to replace u with? Looks like the 5 plus 2x cubed. So you can go ahead and replace u with what u was equal to up there. Okay, so final answer is right here. 1/9 5 plus 2x cubed to the 3/2 plus c. Alright. That's actually one of the more difficult ones in this set, yeah.
Why did you from the ones that get right all of that from there you took it and
Yeah, what I'm using is the reverse of the power rule. So instead of multiplying by the power,
yeah, no, I understand how to do that. It's curious why.
why I did it? Just using rule number 2. This is in the form of u to the power of, I don't know, it says u to the power of n. And so the way you integrate that is by raising the power up 1 from 1/2 to 3/2 and then dividing by that power. So it's, well, you go back to taking the derivative here by the chain rule. We can check it with the derivative. So if I were to check this, even at this stage, it's easier to check it here. The derivative of u to the 3/2 would be 3/2 u to the 1/2. The 3/2 and the 2/3 would cancel out, leaving me with just u to the 1/2. So it's reversing that power rule. All right, example 3. And this one, I don't care if it could be cotangent, it could be tangent, it could be cosine, it could be sine. They all kind of work the same way. But if you have a trig function with an argument other than just x in here, they'll all operate the same. As a matter of fact, in the past, our textbook had a whole list of rules just to handle something like sine, the integral of sine of ax. Okay. And it goes back to what I told you before. You just divide by the derivative of the inside. So some of you could probably do this real quickly right now without a u substitution. What's the integral of cotangent? Derivative of tangent is secant squared.
Oh,
Integral of it. Yeah, so it's negative cosecant squared 7x divide by 7, the derivative inside. That's it. And that's what the rule says. It's just take the integral according to your table. Look at your table. You can find on there, see tangent on there. Which one is it? Or I'm sorry, cotangent. Oh,
must have been like this.
I'm going the wrong way here. Yeah, sorry. I'm getting confused between my derivatives and integrals there. You can see the 9 on there. Yeah, it should be on here. Cotangent, there it is. It's number 13. That's one I didn't say to memorize. I did actually have you memorize. This one, we can derive it, but if you know the integral from the table, so is it number 13? It would be that, and then you just have to deal with the constant in front of it, divide it. So, but that one you don't have to memorize. I'm going to derive this one for you. So, yeah, we're gonna have to rewrite this to derive that formula, but the formula is right there. And if there's a formula there, it's as easy as just matching the formula and then dividing by the derivative of the inside. But I think I wanted to derive this one for you because that was not in my list of ones I do could memorize. We typically don't memorize number 13, 14, 15. You see those in there. So, but here's how they came up with that formula. We're going to rewrite cotangent using its definition. So we'll go ahead and start with that. So the integral of cotangent of 7x dx is equal to the integral of tangent is defined to be sine over cosine, so cotangent is the reciprocal of that. Remember that? So it's cosine of 7x over sine of 7x dx. This is actually a double substitution. But we're just going to do one u substitution. It gets a little confusing with the double substitution, just like it did with the chain rule. All I'm just going to tell you that when you take the derivative of cosine or sine, or integral of cosine or sine, you're just going to divide by the derivative of the inside. So in this case, looking at number 13 on your table of integrals, can you use the information there in terms of what the integral is to decide what u might be? Because u is either going to be the top of this fraction or the bottom, right? You have a guess as to which one it might be? I'm hearing sine. Cosine. Look at number 13. What's involved in the integral?
Sine.
13?
Yeah.
Okay, no, I'm sorry. What else is involved? Yes, there's a sign in there. ln. That's what I was looking for. So we need to make this fit the form of ln. As a matter of fact, there's a whole appendix of integrals that look like 13 through 15 where they all involve ln. So u is going to be, David was right, sine of 7x. So what is du? Well, now we're doing derivative. You have to keep me on this too. I just did the same thing when I initially asked this problem. Yeah. We're integrating. Integrating here, differentiating here. Right? So we got to really pay attention. So derivative of sine of 7x is? Yes, 7 cosine of 7x. That's right, by the chain rule. And then I need to add a dx in here. So let's add in everything we need. I need a 7 in front of the cosine, right? And then what else do I need? A 1/7 out front. Right, so I have 7 cosine of 7x dx. That exactly matches du. And sine of 7x matches du. Yeah, that's going to give us our ln form, yes. I think ln on your table of integrals is number 3, right? So it's 1/7 the integral. Okay, let's replace here. 7 cosine, I'll highlight it here. There it is. All that becomes du, and sine 7x is u. And what's the integral of du over u according to your integral table? Table of integrals. Oh boy. All this derivative and integral stuff. What's 7th ln of u plus c? You see how that works? So we've matched it up. Now you had said there's a sign involved in this.
Yeah.
Okay, where does the sign come from? Well, when I go substitute back in, I've got it. So it's 1/7 ln of, I'm going to move this up a little bit, sine 7x plus c. So if you look at your table there, number 13, it should match it, except for the constant. We had to deal with the constant because, like I said, it's kind of like a double substitution here, but we handled the substitution right up here by putting the 7 in up here and the 1/7 out in front. Yeah.
Oh, that can be fine.
du.
Yeah.
By the chain rule, the derivative of sine was cosine. Match the argument and then times the derivative inside. Just that's how we found it. And that's what introduced that 7.
How do you know the view side of this? Do you only know that about the pictures?
No, well, from experience, I just know that yeah, Maya asked the question, how did I know to call u the bottom of this, the sine 7x? Because anytime you have a ratio of 2 trig functions, and the bottom one is the first degree one, you're going to probably have an ln form. So like if I wanted to prove the formula for tangent 7x, which one is that on there too?
So would you use this way then?
Yes, you would. Yeah, so you would use cosine. Yeah. So if I change this problem and ask for tangent of 7x, you'd have sine over cosine, then u would be cosine. And if they would differ by a negative sign too, you'd have to stick that negative in there somewhere as well. I think that shows up on the homework or another sheet somewhere. So you'll see that one. So, if I ask you a question on this is always tricky because if you look hard enough, you can probably find a formula for a lot of the problems I might ask you about. What I want you to memorize, or what you need to know for the AP exam, is 1 through 11, and then 16 through 18. Like 19 and 20 can be derived, and then 13 through 15 can be derived, and all those, they have some forms involving square root, a squared plus u squared. Those can all be derived as well using different simplifications and things. But those are the ones you need to have memorized. Yeah, 1 through 11, and then what I originally told you for the, in terms of helping you with the antiderivatives on the last test, is what you need to have memorized for the AP exam. And everything else that you might run into can be derived using other things. I mean, hey, if you had it memorized or something, it would hurt. But if I ask a question, then I'm wanting you to use substitution to derive that. All right. Here's another trick here, dealing with the power of a trig function. So we're integrating a trig function that's higher than first power. So it's not going to be on your sheet exactly. I don't think it's on your sheet at all. You can find a formula sheet with this integral already worked out. So once we do this, we're kind of creating a formula for it. But this requires a trig substitution. This goes back to the power reducing formula. So I just gave this to you. I didn't think you'd probably remember it here. But the power reducing formula does just that. It reduces it from second degree down to first degree. And we can integrate a first degree cosine function. So you'll need to write this down. Do you remember the difference? Because I think I asked the question on the worksheet. Sine squared, what's the power reducing formula? Do you remember what the difference is in the power reducing formula for sine squared? Yeah, it just has a minus here. It's the only difference. You might want to write that down now too. The sine squared of x equals 1 minus cosine of 2x over 2. And it still has cosine in it. What's that? We do, you do. It was the one I passed at the beginning of the year. I think I had extra copies of it. Once I get you into groups, so you don't have it still, if you burn, you have a bonfire. Hopefully you didn't burn the book too. It's a little premature to burn the book. So, yeah, I have extra copies of that, so we'll pull that out. You didn't need it as we go through these. So, power reducing. So I'm going to rewrite this as the integral of 1 plus cosine of 2x over 2 dx. And then hang on tightly here. Here we go with some algebraic rewrites.
We do not do this.
Not yet. We're getting there though. We're going to have to do a little bit of a u substitution. Okay, now I'm going to rewrite this again. This is the integral of 1/2 dx plus the integral of cosine of 2x over 2 dx. So I broke that up using one of the properties of integrals that says I can integrate each piece and then add them up. Now, the first part of the integral does not use the u substitution. The second part, we could probably just go with what I told you earlier. You just take the integral of cosine of 2x and then divide by the derivative of the inside. But that's also a u substitution. So the integral of 1/2 dx is 1/2 x. Good. So that part doesn't require any kind of u substitution. Plus, what's the integral of cosine of 2x? Yeah, just sine of 2x, because the derivative of sine is positive cosine. So it's just sine of 2x, but then divided by 2. So if you want to, you could do a u substitution. You would let u equal 2x, and du would equal 2 dx. Okay? And so I would have to add a 2 in here and then a 1/2 out in front. But I think we could probably handle this without the u substitution. If you can just remember, it's the integral of this, which is sine of 2x. No, because the derivative of sine is cosine. No negative in there. That's how I remember it at least. And then divided by 2, and then we also have the divide. Well, we still have the other 2 down here, and then plus c. So it ends up being sine of 2x over 4. But you already had a 2 down here. If you wanted to, you can move that out front. But it ends up being 1/2 x plus sine of 2x over 4 plus c. So remember that the integral of just that is what I have here. So if you just highlight just this part, the integral is this. But don't forget I still have the 2 in there on the bottom of the fraction. That's it. Indefinite integrals are nice. You don't have to go and evaluate it. You don't have to plug anything in. You're done. So this is a whole family of functions that has this as its derivative. So if you were to do a slope field of this, you'd have a whole bunch of short little line segments, and this would overlay on it, depending on what c is. So, yeah.
How do we know if you're finding the derivative or the
You're only doing the derivative when you do a u substitution, and you're finding the derivative of u. Otherwise, the goal here is to integrate or find the antiderivative. Those are the same thing. So when I say integrate, and that's what I'm going to say now, is I want you to find the integrals. That's the same as getting the antiderivative. Yep. So you've been doing it. But
here we found the derivative?
we did here, but no. Here, we just found the integral. We found the integral. So if I were to take the derivative, so if I take the derivative of this, I would get my 1/2. And if I took the derivative of this, I would get this. And then if I put these two together, I have this, which is equal to this. So we have to do the trig substitution to actually get back to what we started with. Any other questions? Good question. Maybe I'll do just one more example, and I want to give you a little bit of time to work on some. Hey, another trig power. Now we're taking it to third degree. Third degree. And there are techniques to deal with trig powers up to, well, whatever you want to go up to. But sine cubed of x. Another trig power one.
Is that supposed to be sine cubed of x equals to
No. The Pythagorean identity, no. Pythagorean identity we're going to use is sine squared equals 1 minus cosine squared of x. So this is a rewrite of sine squared plus cosine squared equals 1. Okay. And you have the other rewrite in terms of cosine squared. So I would expect on the worksheet to see cosine cubed. So you have to think about how you could use the technique that I'm going to show you here to use cosine cubed. So with the even powered trig function, we substituted in the power reducing function. If you had a fourth power one, you could have a couple of power reducing formulas, but you hope that I don't actually do that. You don't want that. It's a mess. Challenge problem for the gifted and talented among your peers. But that's what I'll do for those of you who finished too quickly. I'll give you a cosine to the fourth and say go. I'll hand it to Ethan later. So, so what we're going to do is rewrite this as sine of x times sine squared of x dx. And here's my goal. Here's my thought process, at least. If I'm going to do a u substitution, I need to have a mixture of sines and cosines in my function because they are derivatives of each other, right? So if I'm going to do a u substitution, I have to have a mixture of sines and cosines. So that's what's behind this. So now do you see why I have sine squared one here? So I'm going to replace this sine squared with 1 minus cosine squared of x. So far I have not integrated yet. I'm just rewriting. I'm doing algebra and trig. So there's a little trig substitution. The next thing I would do is distribute. And so I have the integral sine of x minus, I can go ahead and leave the minus sign out in front if I want to. Thinking ahead, it probably would have been better to leave it in. But either way, maybe I'll move it back in here. Let's do that. I'm going to leave it in. So minus, let's go sine x cosine squared x dx. Just leave it in for now. So all I'm doing is distributing here. And I'll go ahead and do the first part of the integral. I'll let you guys do the second part. What's the first part? I'll let you do the first one. Yeah, negative cosine. So that part's done. Now, we need to do our u substitution to handle this. So what do you think u is going to be in this case, using your knowledge of the chain? Yeah, you don't sound too confident, but you're right. It's the higher powered one of the two. So u is equal to cosine of x. Because what we're going to do is make this match the form u to the n, number 2 on your integral sheet. So u equals cosine of x. That means du equals, see why I left the negative in there? Right? Negative sine x dx. Let's highlight it. So this whole thing reduces to okay, du, u squared. Yeah, we don't usually write it that way though, but cosine squared of x. Maya operates by different rules here, but u squared, and then negative sine x dx would we write as du. Yeah, you are a literalist here.
Or would you have click left, right?
Yeah. Are you in a language? Do you do Spanish or French?
No. I mean, I usually
The translation lists on this.
like, I usually do them like
Okay. After you've written it down literally. All right, so negative cosine of x plus, see, guys, I didn't have to add a negative in or anything. The derivative of cosine, which I called u, is negative sine x dx, so it's completely contained in there. So it worked out nicely for me. What's the integral of u squared? Yeah, 1/3 u cubed, and then what do I replace u with? Yeah, put it back in. So it's just 1/3 cosine of x to the third plus c, because this is just 1/3 u cubed, and then I replace u with cosine of x. What's that? It was just the dummy variable. When I integrated it, it went away. Yes. Du, we have to have du substitutes in for all this stuff. And if all this stuff is contained in the integral, then it goes away. So, what's that? Sorry. The 1/3? Using the power rule, I'm raising this up to the third power and dividing by 3. So, this isn't too hard to reverse. You can see that this is going to reverse to this, right? Look at this right here. By the chain rule, and you really have to know the chain rule well. By the chain rule, it would be the 3 would go out in front, canceling out the 1/3. So I'd have cosine of x to the second times the derivative of the inside. There it is. So it's all reversible. So you can check your answer with the derivative every time. So if you're not sure, yeah, it's final answer. If you're not sure, you can check it. Okay. We will stop there for today, and I'm going to let you practice.